Good morning. Before we get into Newton's third law, let's do a little bit of review with a slightly more complicated problem that involves what we learned about mass and weight. So we have a 2.49 times 10 to the fourth Newton Rolls-Royce Phantom. So when we say something like this, we say that an object has some sort of newtons attached to it. What we're talking about is the weight of that object. So the weight of this car, if you didn't know it was a car, is 2.49 times 10 to the fourth power newtons. So if you recall, we remember that weight is equal to mass times g. So why are we given the weight in the first place? Well, if you continue to read the question, we say that the car is traveling in the x direction and it makes a stop, where the x component of the force is negative 1.83 times 10 to the fourth newtons. And we want to calculate its acceleration. So from that we know that force is equal to mass times acceleration, and if we're looking for acceleration we could rearrange this to say that acceleration is force divided by mass. Well, we have the force, but we don't know the mass. That's where the weight comes in. So our weight is going to allow us to find mass because we know this weight it was given and we know g. So if we rearrange this to solve for the mass, we would have weight divided by g. So we can substitute 2.49 times 10 to the fourth power divided by g, and let's go ahead and use 10 this time to make it a little simpler. And when we do that, we find that our mass for this car is 2,490, and that's going to be kilograms. So now we can go in and we can calculate the acceleration of the car. So we know the force. It was given to be negative 1.83 times 10 to the fourth power. And we're going to divide that by the mass that we just found by using our formula for weight. So if we do that, we find that our acceleration in this case would be negative 7.35. So the reason ours is a little different is because we use 10 for g instead of 9.8, which is where this answer came from. And that's perfectly fine because 10, 9.8 is essentially the same thing when what we're trying to prove is how you solve these types of problems. So now let's talk about Newton's third law of motion. So take a second and read the bolded paragraph right here. Essentially what this tells us is that when we have two objects that are interacting, the force that acts on one object is actually going to be equal to the force acting on the opposite object. And why this is important is because it's not very intuitive. For instance, let's say that you are a runner and you want to start your run very fast. You put your feet in the blocks, and as soon as the starter pistol is fired, you set off. The reason you can start a lot faster this way is because you are able to push off of the blocks. But the blocks themselves don't go anywhere. That's because the force on you, even though it's the same force that's on the block, is allowing you to move, while the block itself has other forces that prevent it from moving. So even though it's kind of odd to say that one force on an object is equal to the same force acting toward the other object, so if we have an A and a B, even though the force between these two from the other object is the same, there could be other forces that are preventing it from moving or even allowing it to move in some cases. So it's very odd to think, but we do typically only care about forces that act on a single body that we're interested in at a time. So let's see what that looks like. So let's say your car breaks down. So here's my car. It's just a potato with wheels. And I want to get this car to move by pushing it. So I'm going to push on this car. So what's happening here is that there's a force on the car from me. I'll say it's the force from me. And then there is me over here on the left with a force from the car. And these are actually going to be the same size force. just in opposite directions. So the force of me on the car is equal to negative force of the car on me. So, how then does the car start moving if these forces are equal and opposite? They should cancel out. Well, the answer has to do with the fact that there is some friction that is also part of this equation. The friction that acts on the car is pretty small because it has wheels that can spin. Meanwhile, my tennis shoes are grippy enough that this friction force is going to prevent me from moving while allowing the car itself to move. So, how do these forces compare when I move at a constant speed? Well, they're definitely equal, but they're still equal even when I'm starting it to move. The difference just happens to be that when I'm at a constant speed, so if my v is equal to constant, then the two forces that act on the car are actually going to be the same. And the reason for that is in order to have a constant speed, the total force must be equal to 0. Now remember earlier we wrote that as a sigma f. Now we haven't spent too much time talking about it, but this symbol sigma just means the sum of. Just adding all of these things together. And this is something that you should be able to use over and over in the remainder of this unit. Now let's take a look at a different example of an object just sitting on a table, at rest. Here you have several different diagrams, so let's start from the left. If I'm thinking about the forces in what we call an action and reaction pair, then what I really need to think about is that in order to identify a force, I need to think about what is causing that force. So, for instance, if I'm talking about an apple, I know that that apple has gravity pulling down, and where does that force come from? It comes from the Earth, right? If I wasn't on Earth, there would be no gravity pulling it down. Now, if I am talking about why the apple doesn't just fall down into the table, well, that's because the table exerts some force up on the apple. But those are not the action and reaction pairs that Newton's third law is talking about. The first one, if we talk about gravity, comes from the fact that when the apple is pulled down toward Earth, the Earth is actually pulled toward the apple as well, because gravity is a mutual force. It acts mutually between the two objects that have mass. And so here, that is our first example of an action and reaction pair, because both objects exert a symmetric force on each other. The difference is that Earth is huge. Earth has a gigantic mass, and so it will not experience nearly the same acceleration as the apple would, because that force is equal to mass times acceleration, or even though we have the same force, a larger mass going into the denominator would give us a really tiny acceleration. So this is one action-reaction pair. The other action-reaction pair comes from the apple on the table. So when the apple is pulled into the table, because of gravity essentially, the table has to push back with the same force. And so that's our second action-reaction pair. If I remove one of these reaction forces essentially, say the table, then all of a sudden all I have is the force of the Earth on the apple that's going to pull it toward the Earth. In this case, these two forces are not an action-reaction pair because this is the force that is acting on the apple. It's gravity. There is only one force of gravity that's acting on it in this case. So there can't be an action-reaction pair because it's not acting on the apple, it's acting from the apple. So this is an important distinction, right? We have to say, is this force acting on something or is it acting from something? And if you can't answer that question, you need to be very careful about how you assign these forces. So, we're going to finish this Newton's third law discussion up with a slightly more complicated situation. So ignore all of the arrows for a moment and just look at the situation here. So Michelangelo, the famous Renaissance artist, has an assistant who has been assigned the task of moving this block of marble using a giant wooden sled. He says, when I exert a forward force on this sled, the sled exerts an equal and opposite force backwards. So how could I ever start it moving? no matter how hard he pulls, the backward reaction force would always be equal to the forward force. Therefore, the net force must be 0. So why is this correct or incorrect? The answer has to do with we only care about the forces on a particular object at a time. So if, for instance, I want to move this block, that means that I need a force pulling on the block to be larger than the force of friction acting on the block. The same thing would be true of every other piece of this puzzle. For instance, if we're talking about the person, then the force from his shoes on the ground must be larger than some force of friction that is resisting this. Or in this case, not really friction, just the fact that the sled is pulling backward on me. So how do we distinguish what's going on here? Well, if you look, we have several different pairs of forces that are drawn here. And you can see that they're pairs because of these subscripts that are reverses of each other. So if you see, if I look at the friction acting on this sled, I have a reaction force for the force of friction. So the force of friction on the sled exerted by the ground is, of course, the opposite and reaction force of the force of the ground exerted by the sled. But what's the difference here? Well, when we think about the forces on the sled, only one of these is acting on the sled. And in this case, we also have a force from the assistant acting on the sled. So these two forces are allowing us to move because those are the forces that are on the sled. Then, if we kind of look at the assistant, let's take a look at these two forces. These are the forces that are acting on the assistant. And in this case, they are not going to be equal because they are not action and reaction pairs. So the biggest trick here happens to be make sure that even though Newton's third law tells us that every force has an equal and opposite reaction, that reaction force is acting on something else. And therefore, it doesn't cause us to cancel out in most cases.